In this project, our goal is to design a biomimetic sound coding strategy for cochlear implants that results in neural activity patterns that are closer to acoustic hearing. This project is done as part of the Australian Future Hearing Initiative research, which is a collaboration between multiple world-leading companies. Cochlear implants bypass damaged hair cells. However, due to some technological restrictions, they're not great at restoring important auditory features such as onset enhancement, F0 modulation, and traveling wave pattern, all of which are very important for speech perception. If we have a model of how these hair cells should work, we can use it to mimic the auditory nerve responses with the cochlear implants, which could lead to a better sounding speech or music for cochlear implant recipients. So the first thing we need is a model of cochlea. The model we are using is the Carfax model developed by one of our collaborators, Richard F. Lyon. What you see here is the output of Carfax for the sentence, "The lady is sewing a dress," for all channels across time, and this is what we call a neurogram. It shows which neurons going from base to apex or high to low frequencies are active at each time step and also the level of their activity. Carfax is great at representing auditory features such as the traveling wave delay of the cochlea, fundamental frequency modulations, and onset enhancements in responses of neurons, which are all very important for speech perception. So now that we have our auditory model, we need a way to get neural activity for cochlear implant stimulations. That is done through electrical hearing model. In a typical cochlear implant stimulation, the spectrogram of the sound is mapped to 22 electrodes and envelopes are extracted from those electrodes and used to modulate pulses. This will produce what we call an electrodogram. If we pass these electrograms through an electrical hearing model, we get the neurograms for cochlear implants. The electrical hearing model has two components. One is a finite element model, which we get the current spread from. This will tell us which neurons can be activated when a particular electrode is stimulated across the cochlea. On top of these, we add some physiological properties such as refractoriness and adaptation. If we compare the neurograms obtained from the Carfax model and the cochlear implant stimulation method called ACE, at first we might think that these neurograms look very similar, but if we look at a smaller section, we can see that the cochlear implant stimulation strategy does not represent the traveling wave delay, fundamental frequency, and onset enhancement that are present in the acoustic neurograms. And these are some of the reasons that lead to problems with speech perception with cochlear implants. Our goal is to design a sound coding strategy that would bring these features back and close the gap between acoustic and electrical hearing neural activation patterns. We could approach this goal in two ways. The easiest way is to replace the ACE filter bank, which is the current method being used with cochlear implants, with a Carfax-based filter bank. We use two conditions with the Carfax model. The first is the full Carfax model, and in the second condition, we replace the inner hair cell model in Carfax with a half-wave rectified basilar membrane response. This causes the inner hair cell to be bypassed, which in turn leads to a less strong onset response. This is done so that really strong onset responses don't dominate the electrode activation. The Carfax front-end strategies would work very well if the electrode-neural interface was perfect. However, we know this is not the case, so we need to take that interface into account. This is the framework we are using for designing a sound coding strategy that includes the electrode-neural interface. We get the target neurograms by passing audio inputs to the normal hearing model. We then pass the neural envelopes that we extracted from normal neurograms as the input to the DNN-based sound coding strategy and obtain electrodograms. We pass these electrodograms to the electrical hearing model and generate CI neurograms. We compare these two neurograms through the custom loss function and use the gradients to train the DNN-based sound coding strategy. An intuitive way to look at this is that DNN is learning to compensate for the current spread and refractory characteristics in the electrical hearing model by modifying the neural envelopes from the Carfax model. So I'm going to show some results that shows the Carfax-based methods are promising. If we compare the neurograms obtained with Carfax, the DNN-based method, the two Carfax front-end methods and ACE, in terms of representing the onset enhancement, we can see that the DNN-based method and the two Carfax front-end methods do a much better job at enhancement of the onset compared to the ACE strategy. Also, in terms of capturing the traveling wave delay and the F0 modulations, the DNN-based method and the two Carfax front-end methods do a much better job compared to the ACE strategy. Another way to compare pitch representation and F0 modulations is to look at the stabilized auditory images. The stabilized auditory image is a time-varying representation of the short-term signal periodicity in different cochlear channels, which can be obtained by performing a windowed cross-correlation. The stabilized auditory images here are shown for a 40 millisecond segment of the signal. The x-axis shows the lags and the y-axis shows the frequency channels. From top to bottom, the first figure is obtained from Carfax neural activities, the second is from the DNN-based method, the third is from the Carfax front-end neural activity, and the bottom is ACE. The ACE modulations that we see are not related to the normal hearing, and they are modulated at the channel stimulation rate of 1000 Hz. However, we can see that the DNN-based neurogram modulations align well with Carfax modulations, and the pitch is coming through nicely. The front-end method also aligns well with Carfax modulations. However, there is less temporal definition. These results were from one sample. However, if we look at some metrics over a test dataset, we can get a better idea of how well these methods work. Here from left to right, the first plot shows the structural similarity index loss between Carfax and the neurograms obtained from each method. The SSI loss is a measure of the similarity between structures present in the neurograms. The middle one is the mean squared error between Carfax neurograms and the neurograms from each method. The third one shows the MSE between stabilized auditory images from Carfax and each method. Each of these are defined in terms of loss, which means the lower is better. In each figure, we see four box plots, each showing different methods, which are ACE, the two Carfax front-end methods, and the DNN-based method. We can see that the DNN-based method performs much better than the other three, followed by Carfax front-end methods, and they are all significantly better than ACE. So in conclusion, our goal was to close the gap between acoustic and electrical hearing neurograms. The DNN-based biomimetic sound coding strategy can produce neurograms similar to the neurograms obtained with the normal hearing model. By using sound coding strategies based on Carfax, we can represent the fundamental frequency, onset, and traveling wave delay better compared to ACE. And it has been shown that better onset enhancement or F0 modulation could lead to improvement in speech understanding in cochlear implant recipients. Thanks for listening.